Okay, so you should have this little beauty in your um, classwork. It's not super easy for me to do this typing and talking, so I'm gonna just tell you that you can fill this in. It's a good thing to know all this stuff. It's also in your textbook. Okay, there's a table at the end of this section that has all the information, and it's probably a little bit easier to read it there. But I'm going to go through it on the PowerPoint and try and explain it. Yeah, and we'll go then try and make sure I don't talk too long. Yeah, and then you can do your experiments. So that's the plan, man. So if you want to take notes, you can on this. Otherwise, those of you in the classroom or at home, take it on a piece of paper. You don't have to take it on there, but that would be a good way to review for the test. All right, so predicting products. One of the things that we would like to be able to do is look at our ingredients, our reactants, and kind of think about what should happen in the reaction. Turns out, if you look at the left-hand side, the reactant side, or the right-hand side, there's often some really big clues that can tell you what kind of reaction is going to be taking place. So this is my old sheet. It's just a screenshot of my old one. I redid it on Google Docs for you guys. Okay, so the first reaction is what's called a combination or synthesis reaction. We've already talked about this a little bit, and it's pretty small, but it's basically you've got something plus something, and it makes a single combined something. Okay, now either of these could be a compound, but most likely they're elements. It's possible that it's a compound and an element. The key to recognizing that it's a synthesis or combination reaction is that there's only one product. Okay, that's the biggie. And hopefully that makes sense. We are going to do this reaction tomorrow. So again, we've got another day of reacting in closed-toed shoes. We're going to take a piece of magnesium ribbon and hold it in our tongs and put it in the burner. And it's quite entertaining. I'll demonstrate it tomorrow for you as well. So the example equation is right here. And again, there's a couple of tricky things that I want to remind you of. So magnesium is an element. Oxygen's an element, but it's diatomic. So you've got to watch out when they say oxygen gas. You have to remember it's diatomic. And then what's going to happen is magnesium goes with oxygen to make magnesium oxide. And that reaction, I'm going to erase this now, excuse me. That reaction, even though there's two oxygens on the left, because when you go to the oxygen store, you have to buy them two at a time, magnesium only goes with one oxygen. So you're going to have to remember the stuff we learned about element and families, and magnesium is in group 2, so it has 2 valence electrons. So magnesium gets a +2 charge. You don't have to write this one down, but I just want to emphasize this. Oxygen always has a -2 charge, so when they go together, it's one of each. And of course, this is not a balanced equation, so we have to fix that. Okay, but this is where hopefully you learn, you remember the stuff from earlier. And yeah, okay, so if we've got one magnesium on the left and one on the right, it's golden. But we have 2 oxygens and 1 oxygen. The only way we can fix this is to put in a coefficient. So what does that mean? Now I have MgO and MgO. I have Mg and I have OO. But now I have to balance it. So what else am I going to do? You can see it on the screen. I'm going to put a 2 here so we have a second magnesium. Okay, now we have all the same pieces on both sides of the arrow, and we have a balanced equation, and we've obeyed the law of conservation of matter. Right? Good on combination? Questions? All right. Decomposition is basically the opposite. So in synthesis, we're putting stuff together. in decomposition, we're taking it apart. Okay. And the example they use, we will not be using as the heating the mercury. So the general equation this time is some element R, some element S becoming, this compound RS becoming elements R and S. Again, it could be that one of these is a compound, which is going to actually happen in our decomposition reaction because we're going to use, and you're going to do this today, you're going to use hydrogen peroxide and decompose it. And it's going to make water and oxygen. Okay. So it's possible that one of these could be a compound. Sometimes, as in the case of this example from the book, it's both elements. Okay. So a single reactant tells you that you have a decomposition reaction that you're looking at. So again, there's different kinds of mercury, mercury 2 and mercury 1. And this one is mercury 2. And it is a mercury 2 oxide. Lots of ores, metal ores are oxides because oxygen reacts with like everything. Makes solid mercury, or excuse me, liquid mercury, it's not solid, and oxygen gas again. So again, you've got to remember that diatomic oxygen, because the temptation is to go, oh yeah, mercury, Hg, oxygen. Oh, you've got to remember it's diatomic. And the same issue again, we've got one oxygen on one side and two on the other. The only way to fix that is to put in a coefficient. That gives us 2 oxygens, but now it also gives us 2 mercuries. So we just put a 2 here. And now we're balanced. So I have I just remember we have chickens and we give away eggs because we don't eat them all. And this is my dumb analogy for the oxygens, okay? When you go to the store, can you buy just 1 egg? No, it doesn't matter that your recipe only calls for 1 egg, right? It's irrelevant. 1 egg, 3 eggs, whatever. You still have to buy them 12 at a time. I guess you can buy them 18 at a time, of course, and you can buy them, I think some places sell them 6 at a time, but you can't just buy 1 stinking egg. So it doesn't matter, you know, that I only need 1 oxygen in the compound. I have to buy them 2 at a time. Okay, so silly little analogy, but hopefully that makes sense. All right, single replacement. And they use weird little symbols because they're doing examples. They're trying not to get you confused with element symbols, although, of course, S is an element symbol, but that's all right. So single replacement reactions, you have to look at the activity series. And we're going to do a single replacement reaction today. And I'll talk more about that when we get to it. But for this one, they've got an element by itself in a compound. And then it becomes a different compound and a different element by itself. Okay, so this particular example would indicate that we have a metal that we're replacing. Why do I know that? Because it's always metals at the front, right? They form cations. Okay, so it can be, I just want to emphasize, it's possible that the element will replace the anion, the nonmetal. But in this example, because it's at the front, I know that it's the metal. So if you recall, we got a list of, oh, you know what? I should give you a copy of that too. I usually give you guys a copy of the activity series. You can have it. So hard to hand out papers when you can't lick your fingers. Figured out how to open up the vegetable bags at the market though. And then just go over where they spray everything. There's a little bit of moisture over there you can touch. Life hacks. Thank you. You're welcome. Okay, so those of you at home, I will get a copy of this into the reference material as well. So again, you've got this activity series, and you have to look and see, is this metal higher than this metal, for example? So again, lithium wins, gold loses, okay? Gold never is going to be able to bump anybody because it's at the bottom. There's some other stuff hopefully we'll get to in the last week or so on solubility, but this is the focus, this top little thing. I remember all the halogens are always, they're in order as on the periodic table. So in this case, we've got potassium. So let's just look at this real quick. The element potassium and water. And you've seen this reaction. You've done this reaction, okay? And so potassium's a metal, and in water, hydrogen's acting as the metal. Now, this is also a really weird thing, and probably most teachers aren't going to show you this, but think about water as HOH, right? Hydrogen and hydroxide. Okay, those are that's your positive cation, and then your polyatomic anion, all right? So can potassium bump hydrogen? Well, I have to look at my handy dandy table, and I find hydrogen, and they have it in caps on here. Hydrogen, and let's just see. Oh yeah, potassium's way at the top. So potassium's gonna knock hydrogen off of the water molecule. What's gonna happen is potassium is gonna go with the hydroxide. Remember, potassium's a +1, it's in group 1, hydroxide's a -1. And that's gonna leave hydrogen. Okay, again, you've got to remember that hydrogen is diatomic when it's an element. It doesn't have to have 2 hydrogens in compounds, but it has to be when it's just hydrogen. And again, that has to do with hydrogen's dots, right? The valence electrons. If it has 1 dot, it can share 1 electron and make 1 single covalent bond in the hydrogen molecule. Okay. So solid, liquid, aqueous, it stays dissolved, and then of course the hydrogen's a gas. Okay, and ours didn't like quite that good, but if you remember the purple flame on the surface of the dish weeks ago. Okay, again, this isn't balanced yet, so we have to figure that one out also. Since we have to have 2 of these, that means 2 water molecules have to come apart. Oh, they're not going to be pluses. Okay, and so I'm going to have to do this and this and this. I need 2 hydroxides to go with the 2 hydrogens. Okay, the hydrogens are coming from the water, and that leaves hydroxides behind. And I have to have 2 water molecules in, HOH, and then I have to have 2 potassium. So everybody gets a coefficient of 2 except the diatomic gas. Good to go. How are we doing on time? I'm going to do this one because this is the type of reaction that we did. So double replacement, I'll save the others for tomorrow so we can get going. Double replacement reaction, that's my innies and outies. So they have RS, and they're putting the charges on there just to remind you. TU. Okay, and again, this is really silly, but it works. Okay, I do the innies and I go backwards. Why? Because the cation has to be listed first in the compound and the anion second. And then I do the outies part. Okay, so what have we done? We have ionic compounds that dissociate. Okay, this is almost always in water. So it's almost always, aqueous. Okay, and this is what we did with the little dropper bottles. The two solutions mix, the positive and negative pieces from each can mix, and they can switch partners. Now, sometimes you get a precipitate for one of them, and sometimes the others stay in solution. Sometimes they can both form precipitates. Sometimes nothing happens and they both stay aqueous. Yeah.
Does the positive always have to come before the negative?
Yes. So again, metals on the left, cations on the left, losers on the left. Everybody, it's on the periodic table. It's in the formulas. It's always the metal first.
Okay.
Yep. And I wish someone had told me that in school. That's why I make a big deal about it. All right. So this example is potassium carbonate and barium chloride. The solubility stuff down here helps you to predict which one's going to be the precipitate. Barium's almost always insoluble. You don't have any way of knowing that, but I'm just telling you. And potassium is always soluble. All the alkali metals, the first column metals, whatever they form a compound with, always soluble. End of story. Chlorine is always going to be soluble as well. So anyhow, we'll talk more about solubility stuff later. The potassium, remember, is a +1, carbonate's a -2, so you need 2 potassiums in that compound. And that's convenient because barium's a +2 charge. It's in the same family as calcium and magnesium, and it has 2 chlorines, so very handily. You have to watch out. It's not K2Cl2, right? It's +1 potassium, -1 chlorine, and then it's 2 of them. Okay. And then the barium and the carbonate go together 1 to 1. So the only place that you need a coefficient in this reaction is in front of the potassium chloride, but it was indicated with the subscripts on the formulas. Right, so you probably want to have that sheet of ions handy as well, just to think about things. I'm not going to be testing you yet, but we're going to do some practice ones tomorrow. Well, yeah, I'm not sure. Can't believe it's like hardly anything left of school. My gosh, this year's felt like so long, and now it's like almost done. It's nuts. All right, questions on those? Okay, so any questions from home? Beautiful. All right, so I'm going to pull up our lab and see if I can find it. Actually, I forgot to open that up. Oh. Okay. Every period on Friday, people were pulling everything out of their drawers. You've got to focus and just not pull everything out of your drawers. So hydrogen peroxide is going to be used today. And we're going to be testing for, I'm not going to have time to go over those, so we can get going here. You're going to be using a catalyst, okay? So it says 5 to 10 milliliters. Don't measure it. Just fill your test tube about half full, okay? A third to a half full with the hydrogen peroxide. And then this little vial has manganese dioxide in it. It's a little black powder. And this is the catalyst. Remember, catalysts speed things up, but they don't get incorporated into the product. Use a clean splint as a little shovel. Okay, you do not need much. Hardly any of this stuff is needed. Just barely get some on there. Put that into the test tube with the hydrogen peroxide. And then we're going to cover it up with a watch glass again. Okay, and you let that react without breaking your watch glass. Okay. maybe. There we go. Okay, so let it react for a while. It says 15 to 30 seconds. You probably want to wait closer to a minute. Okay, and then we're going to predict that this is oxygen. Okay, so this is going to be a glowing splint. James, your mouse, please. So a glowing splint. And there's pencils and pens in the back if you need one. So H2O2. Is going to form water. And oxygen gas. Okay, and so we need a glowing splint for that. So remember, you light the splint and then shake it out and then put it into the mouth. Try not to touch the edges of the test tube because it's probably wet. But yeah, I got mine to relight 5 times on the thing that I recorded for these guys. So you may or may not. It depends on how long. If you don't get it to relight, just cover it and go on to the next reaction. And then you'll be able to probably test it afterwards. Zinc and copper chloride. You're going to look in this little container. There's some zinc at your things, and then there's a well plate. And so you're just going to put a little bit of zinc in here, and zinc is not reactive. You can just touch it, just put a little bit into the well plate, and then you're going to add 5 to 10 drops of the copper chloride. Okay, so remember to make observations. Okay, so remember before, during, and after. And then you probably won't be able to tell anything on temperature, but you can try and feel through the plastic. Okay. All right, this stuff should not go down the drain because of the metal. So when you're done, oh, my wool is coming off. When you're done with the zinc and the copper chloride, just clean it up here and then rinse out the well plate. That's the other thing I want to tell you too about the hydrogen peroxide and the manganese dioxide. You want to put it into this bottle, not down the drain, but then rinse out your test tube. And then the last one, if we have time, is also going to happen in the well plate. There's a bottle of silver nitrate and a bottle of NaCl solutions, and put a couple of drops of each into one of the little plates. It says 5 drops. That might be a little bit too much. Please, please, please do your best not to touch the droppers to anything that's in the well plate, whether it's the solid zinc or the other solution. Okay, don't try not to keep the tips up above it, so you can not get contaminated. Okay. All right, questions. Okay, so I'm going to let you do those 3 if you can, and if you can't, that's all right. And go ahead and goggle up. If you're in shorts, I strongly recommend that you wear an apron. We're not doing anything too crazy tomorrow. You will have to wear an apron. What's that? Yes, you can leave me. So those of you at home, you can look at my recordings that I posted and get those observations filled in, and we'll go from there. Okay. Any questions?